Hello sir, so this video is going to be to explain my project. So to give us a quick description about my project is to design a safety system that's specifically for professional grade servers that have large scale computing modules that are kept in isolated rooms in industries. So what this has is there are three levels in the system. System one is to make sure there is a proper tracking using the program and the interface. Make sure there's real-time tracking of the temperature and humidity in the room. Next is to alarm the concerned authorities if there is some kind of an issue that happens. The alarm would go off. Third situation is have its own autonomous defense system in such a way that it can take out the fire in its initial stages itself, essentially saving us from having a catastrophic fire incident. So I'll be showing you how the circuits have been made. One small disclaimer is that the first part of the video where I show the mega alarm system, it works perfectly. However, in the second system where I designed the whole thing and 3D printed it myself, there are a few issues that I faced, such as for tolerance and the precision in manufacturing. What happened is because since these are not made for precision, these are made out of plastic and everything, the gears and everything. What happens is there's a slip and lack of very bad tolerance. Hence, the gears might not function as it's supposed to be. However, if you review the code, and if the tolerance issue is solved, what happens is you can see that the system would work perfectly. So, hello sir. So this is to explain the circuit diagram and how this whole thing works. Uh, as you can see, first to explain the circuit diagram, there is an Arduino Mega. There are almost 19 wires powering the LCD. There is a light bulb which emits and which is always on to make sure to help the person understand that okay, wait, as you can see, this thing is glowing. So and the next to it is a red light, which is to show code red and there's something wrong with the system. And not this system, as in the server, there's some kind of abnormality happening in the server system. And then there is a buzzer. Then there are resistance wires to connect them all together, and this whole thing runs on power supply like this. It doesn't take a lot of energy to power something like this. So how this works is when the temperature or humidity rises above a certain temperature or a certain threshold, it shows that reading here. Like if I increase the temperature, something like that, it would show an immediate change in temperature. Temperature is not that easy to change because I can't change the temperature on the sensor just by blowing into it. Humidity I can easily change. So as you can see, humidity has shot up altogether because it's so much hydrogen I've blown into the sensor. So this is how the first and the second system works. First system is to directly monitor this in real time and make sure everything's going smoothly by a person. You can have it on screen display near a security or something like that. Humidity can detect anything. It can detect some kind of changes it's there, or change in atmosphere. Anything can be detected using humidity. And temperature is just to make sure that everything's going smoothly. It's an added benefit. So that's all about second system. Now moving on to the next system, which is the which is the main part of the innovative system in this, and that is right here, as you can see. Now this is the last system, this is the box. This is a 3D printed box. The outer surface is, the inner box is basically foam, I've glued it together. Why there's specific reasons for PETG and foam, I'll be explaining as we go. Uh, this is the MQ2 gas sensor that is supposed to be used for this system. Now there are three types of monitoring. One is to monitor if there is any gas, another is to monitor the humidity and temperature. Either one of these if we have either one of these things, it will still be more than enough to monitor. However, my approach is to make a cheap and best fail-safe system that would act regardless of what the situation. It would do some kind of damage control at the early stages, so it can control the whole fire going out of control. So that now comes to the mechanical part of this. As I said, this is a 3D printed box. This inside box is a foam box. It is supposed to house CO2 in it. Now this gear system, it's kind of powered by two DC motors, BO motors. They move the spur gears that are connected to the motor, moves the pinion gear up and down in order to move the box, the outside inside box outside or in, just like that. So that's how it works. Now this how this works. So this is an L293 motor shield, and underneath is powered by an Arduino Uno. Now reason for this is because I'm almost giving to almost 12 volts, 10 volts of energy to this thing, not 10, around 10, 12 volts. So I need more than the Arduino Uno, because Arduino Uno can't handle that kind of force. So I need a motor shield, and also to handle the power of these two things. Now I'll connect the batteries and take input from the laptop. Now the reason I've connected a data cable is just to show it on the data on the serial monitor. Otherwise it can still work autonomously without the thing. As you know, this is a fail-safe system. It needs no human intervention and it will work on its own. Now I'll put the battery back in place. As you can see, the light over here has gotten a little more brighter. So now I'm going to show how the system works. Right, so as I've already explained the circuit diagram, this is how it goes. And now you can see on the serial monitor, what happens is you can see the threshold going around 374, and the second it hit 380, it moved, the motors moved. So that's how the principle works. So this thing goes in. Okay, so as you can see on the screen right now, the threshold value is showing around 292 and it is stable over there. Now I'm going to take an incense stick to simulate smoke and see what happens. So we have the smoke coming up. All batteries are in place and the power is working. So as soon as it starts, the density starts increasing. It's now at 328. Since okay, so now in order to show this, I have an incense stick that is producing smoke. Now because of the smoke, the gas sensor has detected it and it has released the CO2 sensor. Now as after it releases, it would go back up. So now the reason it's coming down, did not fully go up, is because the few reasons why I couldn't exactly show it to move completely up and down is mainly because the tolerance of this, as you can see, no matter how much tight I make this, these are like really tight tolerances, and but still, since the material is flexible and I can't afford a material that's like metal or something, so what happens is it slightly gives a small kind of jump and it slips through the gears. So it misses the gears because these are plastic and used for prototyping and student projects. When we make it with an actual thing, the metal gears would precisely go in and go up. So, and if you can verify the code, and you can see the delays are exactly given in order to make sure it goes up. And since for metal gears it will be more precise, so it will work out fine. Here, however, the working was perfect. The prototyping and how it worked out when it crossed a threshold. Keep in mind the threshold I've given has changed and varied because of the instance team being worked for more than half an hour, which what happened is the threshold in the room kept changing. Now now the question would be, would this thing affect a room when all these things that happened during the video would affect the room? Thing is, it won't, because this is a place where people don't like this system is made for places where people generally don't go in. It's like clock room or something like that. Clock room, sorry, storage rooms. So that's where most of the fires happen, and then short circuits happen. And so if you install a system like this in that place, what happens is it would this system would make sure there's some kind of defense mechanism. Alright, so this is system 1, which does the active tracking and sending data and all that good stuff. This is a completely embedded system that works on its individual power supply using batteries. Few of the design aspects that I have to mention is that this is a initial prototype for this model. Obviously, if I were to sell it as a product, this wouldn't be this long, and these gears would be made out of metal, which is what the reasons I was mentioning in the previous part. So as you can see, this moves like this and it slips gears. So just to recap the functionality, what it does exactly is that once the MQ2 sensor detects it, this would automatically send a data signal to the Arduino, which would simultaneously rotate both of these motors in opposite directions to push the pinion gear down. Once the pinion gear comes down, what happens is you have this casing. So the final part of this design is the casing alone. Now this casing is made using foam. There is a very good reason why this is used. This not only is it if it was supposed to be an actual product, it would still be foam. Why this is foam? Allow me to explain it. So this casing, how this works is that you have these small tiny holes in here, as you can see. Just for depiction, these pipes, this is just for depiction. Obviously, if it is a high pressure CO2, it would be of much higher quality pipes. It would go through here and it would store the CO2 in here in this container. So what happens is once it gets released, it would release the CO2. So all of these systems are well and good, and most of these the design using gear systems is new. So this is an attempt to find that. Now the most exciting part of my design, but not exactly something that people would notice, like it's not a complex part of this design, but the most fascinating part is how simple this design is. And it's basically just using a material aspect of material as the design, like you selecting a well researched material such that it can easily withstand the force of the CO2 pressure. It wouldn't be high, you don't need high pressure because it's going to be confined spaces, you just need to release it. So what I've thought is we need to use foam. So why foam is because I could have used a lot of materials, but why foam is because foam is something that would easily catch fire. Okay, so now it might be weird to think that why is that something that would easily catch fire being added to this system. Well, let's say that all of these systems, the temperature and the gear system failed for some insane reason, it is just exploded. So I need something that would still function in that, which comes, this is a kill switch. So if the system comes to this stage of the fail safe, what happens is it would be a one time. You'll have to replace this part of the system. So how it works is that foam is, as I mentioned, it's already a highly flammable material. So what happens is, let's just say that this system is attached like this, and it's supposed to move out like this. Okay. Now for a very weird reason, let's just say that this system failed, and there's no way for the CO2 to come in. That's why the foam is coming. So essentially what it does is, it would see the fire is spreading, there's nothing to stop it. The only thing that was supposed to be stopping was the CO2 that's coming out of it, which would be sprayed over the fire to reduce it. Now what happened, there is no access to this. So what happened is, this foam would easily catch fire and it will blow out. What this has inside is CO2. So what happens is, CO2 will start rushing out because the casing has been burnt. So the CO2. So basically what it does is, it acts like a mechanical sensor. Mechanical sensor as in one time use fire. It detects fire. It basically catches fire out by itself, and it then executes the system, which was what this was made for. And now you might be thinking this would burn, but this is 3D printed just for this project. But if it were to be an actual product, this whole casing would have an enclosure for all these components. Like, it would be internally, it would be covered with something that is highly resistant to heat and rust. So that would be covered, and the possible materials for that is covered in the literature survey, in the report. Okay, so moving on. So the final system demonstration is actually very easy, as I mentioned. So let's say fire is raging out. We have fire. It would just catch fire just like that. As you can see, it's immediately melting out. So it's not catching fire, but it's just melting out. So it would just melt out. As you can see, this thing would just keep melting and burn itself out, which would make way for the CO2 housed inside to just I think I've made my point clear. So you can see this thing is completely, and it is rigid, very hard and very rigid. It won't break. So I think that proves it can withstand, like high density foam. It can withstand the pressure, but it can't withstand the heat. So it works perfectly as we need in this system. So this material selection, I think, is one of those small simple design aspect that could make this system highly reliable. So that's it for the video. Any questions, please put them in the comment section. I would immediately address it. And thanks for watching. I hope you like the project, and thank you.